Hello everyone, I'm Anton Vitlugin, a research fellow at Nanyang Technological University in Singapore, and today I will present our recent results where we demonstrate anti-Hong-Ou-Mandel effect with entangled photons. And on this project I work with my colleague Rusyan Guo under supervision of Cezare Sochi and Nikolai Zholodev. Photons are bosons, but entangled photons allow us to implement both bosonic and fermionic type of interference. So on this figure, we have two photons, which occupy two optical modes, alpha and beta. The total wave function of the photons contains two components. One describes polarization state of photons, and the other describes special degree of freedom, or how these photons are distributed between the optical modes. So if polarization degree of freedom is symmetric, here I give an example of symmetric Bell state, then special wave function should be symmetric as well, so that the total wave function is symmetric. And this symmetric special wave function describes bosonic type of particles. And if we interfere these photons on a beam splitter, they coalesce, so they leave the beam splitter through the same output port, either this one or this one. And in the Hong-Ou-Mandel experiment, we place single photon detectors at each output port of the beam splitter, and we measure coincidence count between these detectors as a function of the relative delay between time of arrival of the photons to a beam splitter. So when the photons arrive to the beam splitter at different times, so they do not interfere and split randomly between output ports, and we have some reference level of coincidences. But when photons overlap on the beam splitter, they interfere and Hong-Ou-Mandel effect takes place, and we observe the dip in coincidences. And this phenomenon has rich areas of application. So as it was proposed in the original experiment by Hong-Ou and Mandel, and actually used nowadays in the experiments, it can be used for precise timing measurement. Also, this phenomenon is used in proposal for quantum metrology and lithography applications. And of course, it is a basic phenomena for implementation of linear optical quantum computation schemes. And if polarization state is antisymmetric, and one of the Bell states is antisymmetric, it should be accompanied by the antisymmetric special wave function. And this special wave function describes the fermionic type of particles. And if we interfere these photons on a beam splitter, they will anti-coalesce, so they leave the beam splitter through different output ports. And as a result of this, we observe peak in coincidences instead of the dip for bosons. This ability to switch between fermionic and bosonic type of interference of entangled photons has many applications as well. For instance, in quantum information, let's say dense coding, also for simulation of physical and chemical systems, both of bosonic and fermionic types, and for heralding of entanglement and its distillation. Let me summarize. Bosons coalesce on the lossless beam splitter, and we observe dip in coincidences, while fermions anti-coalesce, and we observe peak in coincidence counts measurements. So what I showed today, that we may completely reverse these output statistics, and bosons actually may anti-coalesce, and we observe peak instead of the original dip, while fermions may exhibit coalescent-like behavior with dip in coincidence counts measurements instead of the original peak. And to do so, we replace the lossless beam splitter by the special case of the lossy beam splitter with 50% of loss. And here you may see theoretical works on this phenomenon. So the bosonic type of loss interference was analyzed in the paper by the group of Loden. So in this paper by the group of Markier, they analyzed fermionic type of loss interference. And recently we developed unified description valid for both bosonic and fermionic states, and for other quantum states as well. First of all, let me explain how we run the experiment. And at the first stage of the experiment, we prepare and measure the bosonic and fermionic states of entangled photons. So we generate entangled photons in spontaneous parametric down conversion, one photon from the pair is sent upwards on this figure, and second photon is sent downwards. They pass through bandpass filters to ensure their spectral indistinguishability, and one of them passes through the Bell state control, which is a set of wave plates. And later each photon passes through the analyzer and is detected by a single photon detector. And it is a standard verification of entanglement. So in this type of measurements, one of the analyzers is fixed at one of these four angles, 0, 90 degree, plus and minus 45, while the second analyzer is continuously rotated. And the coincidence counts between these two detectors is measured as a function of the angle of this analyzer. So here you can see these four curves, and as you can see, all of them are of a high visibility, which is only possible if photons are entangled. And from these curves we may calculate the Bell parameter, which is 2.63 for the symmetric bosonic state. And I remind you that the Bell parameter should be higher than 2 for entangled photons, and its maximum value is 2.88. So next we prepare the fermionic state and measure it again. And as you can see, the correlations in horizontal and vertical basis are exactly the same as it should be for bosonic and fermionic states, but correlations in the diagonal and anti-diagonal basis are opposite. And again, from this measurement we extract the Bell parameter, which is 2.6 for this state. Next, we counter-propagate the entangled photons and interfere them in the middle of the interferometer. To observe the Hong-Ou-Mandel effect, we place the lossless beam splitter, which is just a dielectric film with transmission of 60 and reflection of 40%. And to measure the anti-Hong-Ou-Mandel effect, we use the Lossy beam splitter, which is a transparent substrate with deposited ultra-thin absorptive layers on both sides. And this structure has optical response close to what is required for the observation of the anti-Hong-Ou-Mandel effect. And the outgoing photons are directed to single photon detectors on both sides. And in the experiment, we scan the position of the beam splitter around the center of the interferometer, thus changing the time of arrival of the photons. And we measure the coincidence counts between these two detectors as a function of the beam splitter position. Let me come to the results of our experiment. So here on the left I show the schematic of the experiment. So in this case we interfere two bosons on the lossless beam splitter, which has two output ports. Here in the middle you can see the expected output photon number distribution, and for the case of interferent bosons we expect to find either two photons at output port 1 or two photons at output port 2, and this results in the observation of the dip in coincidences. So when we replace the lossless beam splitter by the lossy one, the output photon number distribution changes drastically. And here is very counterintuitive phenomena takes place, namely probabilistic two-photon absorption. So the two photons are absorbed with probability of 50%, so with this 0-0 state, while in other cases both photons are survived. And if they do so, they can be found with a small probability at the same output port, port 2 or 1, but with a high probability they will be found in different output ports, and this results in the observation of the peak in coincidence counts measurements. And here we zoom in and show that we crossed the classical limit. It is a couple of works where people observed anticoalescent behavior of bosons. So first of all, in the group of Marquet, they observed the peak in coincidences when interfere two plasmons. Plasmons are bosons. So in the recently published paper by the group of Zhang, they interfere two non-entangled photons on the grating metasurface and observed peak in coincidences as well. And if you attended yesterday's session on quantum measurement 1, you may see this talk of Max Erhardt. where they, first of all, they use polarization, degree of freedom, and a single waveguide for beam splitting. And this coupled waveguide structure allows them to control the losses, and they observe these peaking coincidences. So our approach differs from these works. First of all, we use entangled photons, and as we do so, we originally designed the experiment and the beam splitter not to be sensitive to polarization degree of the photons, which is crucial. And also we concentrated on achieving the output photon number distribution. So to do so, we perform this kind of circle of transformation, where we start with the counter-propagating photons, then we switch to the basis of quantized standing waves, perform non-unitary transformation on this basis to restore the required output photon number distribution, and when we come back to original basis of propagating photons, we observe the anti-Hong-Ou-Mandel effect. With entangled photons, we may also implement fermionic interference. So when we interfere fermions on the lossless beam splitter, we expect to find one photon at each output port of the beam splitter, and this is the reason why we observe peak in coincidences. When we replace lossless beam splitter by the lossy one, the very quantum phenomena happens again, namely deterministic one photon absorption. So one photon from the pair is always absorbed, and the survived photon is split equally between the output ports, and this is the reason why we observe the deep in coincidence counts measurements. And again, we crossed the classical limit. So let me summarize the results of our experiment, and you can find it in this preprint. We interfered entangled photons on the lossless or lossy beam splitter, and for the lossless beam splitter, we demonstrated bosonic and fermionic Hong-Ou-Mandel effect, while for the lossy beam splitter, we were able to completely change the output statistics for bosonic and fermionic states. Here I conclude. We demonstrated the anti-Hong-Ou-Mandel effect with entangled photons for the first time. We demonstrated it for bosonic and fermionic states, and in general, it may be considered as a control of the photon statistics assisted by dissipation. This is our preprint. This is my contact in case you would like to have a discussion. Also, let me advertise you 2 more talks from our group, which happened yesterday, but if you have an opportunity to watch them, you are very welcome. Yeah, and thank you for your attention and this very nice conference.